Welcome back. In today's video, we want to design a circuit that can amplify the difference between two voltage signal by a gain of 50 using 5% standard resistor values. So we can draw our circuit. So our difference amplifier circuit has a voltage signal V1 connected to the positive terminal of the op amp. We're going to call that V plus. V minus is then connected to V out via R2, and V2 is connected to V minus via R1. So here we have our difference amplifier circuit. However, if we go ahead with this design, we're going to get two different amplification factors multiplying V1 and V2. And in order to get the difference of V1 and V2 multiplied by a common amplification factor, we have to use a voltage divider network between V1 and V positive. This voltage divider network can be used because the current entering the V plus terminal is 0. So we're going to add that network. So that's a voltage divider network, and we're going to call it A. So that means the voltage at A is going to be the voltage at V plus. So if it's a voltage divider network with R1 and R2, so let's just draw that network out. So this is the network that we have for a voltage divider network. And that's A. So this is R1, this is R2. We use R1 and R2 in our voltage divider network because in order for the difference amplifier to have a common gain factor, we have to have, for us to acquire R2 over R1 multiplied by the difference between V1 and V2, we have to have the ratio for the attenuation network and the feedback network equals the same or equal. So that means well, let's not erase that so we can make that a little bit more clear. So we have to use the voltage divider network in order to acquire this expression, which that's what we're aiming for. So V out should ultimately equal this. So as you can see, design a circuit that can amplify the difference between two voltage signal. So if we are using R1 and R2, we want a common factor of R1 and R2 to multiply the difference between V1 and V2. So the voltage at V positive. So let's just start by setting V1 equals to 0. So we're going to use superposition to find the V out here. So if we set V1 equals to 0, we then have that V1, well not V1, but V minus is equal to V positive, which is equal to 0 volts. So now we set V1 equals to 0. So we're going to cross that out. Now we're going to use superposition to find V out, and we're going to call that V out X. So if we set V out equals to 0 and find the voltage at V minus with reference to V2, and then set V2 equal to 0 and find the voltage for V minus with reference to V out. So for this, we're going to get that if V out equals 0, we then have V minus. And let's now do it. Well, I think we should go ahead and do it like that. So V minus is equal to, the voltage at V minus is equal to, and if in this case we set V out equals to 0, we then get R2 over R2 plus R1 with reference to V2. And then if we set V2 equals to 0, we can find the voltage at V minus. And we're using superposition, so we're adding them together. And that's going to be the voltage across R1. So by voltage division, we get R1 divided by R1 plus R2 times V out. Earlier we stated that V minus is equal to 0. So if we set V minus equals to 0, we can then solve for V out. And as we said earlier, we're going to call that V out X. So that's going to equal to minus R2 over R1 times V2. As you can see, by setting V1 equals to 0, we end up with a an inverting amplifier, I should say. So we know that if we set V2 equals to 0 and then keep our V1 voltage signal, we're going to end up with a non-inverting amplifier. So we can go ahead and do that. So here we're going to set V2 equals to 0. Let's do that. So V2 is equal to 0. So if V2, this is 0 volts. If V2 is equal to 0 volts, the voltage at V plus is going to be, so this is what we're doing. So V minus is equal to V plus, and that's not 0 volts anymore because we have a voltage signal V1 connected to the V plus terminal of the op amp via a combination of resistors. So the voltage at V plus is going to equal to the attenuation factor of R2 all over R2 plus R1 times V1. So V1 is being attenuated by the combination of R2 and R1 by a voltage divider combination. So we can then say, by setting V2 equal to 0, we can find the voltage at V minus. And by finding the voltage at V minus, we can find V out. So the voltage at V minus is going to equal to, because V2 is set to 0, we can use voltage division. And that's going to be the voltage across R1. So by voltage division, we have R1 plus R1 divided by R1 plus R2 times V out. Earlier we stated that V minus is equal to R2 all over R2 plus R1 times V1. So if we set that equals to V minus and then multiply or just simplify, we then end up with the following. So V out Y is going to equal to R2 all over R1 times V1. And because we're using superposition, we can add Vy and Vx together, and we end up with V out, which is equal to R2 over R1. So we factor out R2 over R1, our common multiplication factor or gain factor, which we needed in order to multiply the difference between V1 and 2 by a gain factor of 50. V1 minus V2. And that is what we were aiming for, which we see is the same thing that we have up there. So now that we know that our gain factor will be achieved by R2 over R1, we can then go ahead and find, well, not find, just pick two resistors of 5% tolerance. So if I pick R2 to be 750 kiloohms, I then get R1, which I should probably just write that. So the voltage gain is equal to R2, R2 over R1. So then R1 is going to equal to 15 kiloohms. So here we see that by using the 5% tolerance resistors, we can use R2 750 kiloohms and R1 15 kiloohms, and we'll get a voltage gain of 50. And by designing our difference amplifier circuit with a attenuation network, we then get a common R2 over R1. And by doing that, we can see that we can amplify the difference between two voltage signal by a gain of 50. And that's it for today's problem. So I'll see you in the next one. Bye.